Hello and welcome to our presentation on the transport layer of Atsc 3.0. The Atsc standard is a bundle of internationally accepted digital standards built to work together in an IP-based network. The only part of the standard that is truly unique to Atsc is the transport or physical layer. This is the layer that enables data transport through the air. Today, three international experts will give you an overview of this transport layer. First, Joonyoung Park, VP and Fellow at Digicap, will put the transport layer into context with an overview of the head-end chain architecture, including the encoder, mux, scheduler, and exciter. Then, Adrian Murtaza, who is Senior Manager of Technology and Standards at Fraunhofer, will talk about video and audio codecs. Finally, Jason Justman, Distinguished Engineer at ONE Media Sinclair Broadcast Group, will talk us through broadcast and broadband delivery. Let's get started with Digicap's Joonyoung Park.
My name is Joonyoung Park. I'm from the Digicap. At the Digicap, I am doing the home gateway development and other engineering the duties. You, Adrian?
Hello, everyone. I'm Adrian. I'm together here with Joonyoung. We will have a look a bit more into details on the transport format for Atsc 3.0.
Okay, let's start. Today we will give you some introduction, a very high-level introduction on the Atsc 3 transport technologies. So myself and Jason and Adrian will be talking about that topic. So as you can see, this is a typical the Atsc 3 protocol stack. What we will be talking about is a transport layer, the above the UDP and TCP layer and below the application layer. First, I'll be talking about high-level architecture of Atsc distribution chain and how architectural components within that distribution chain connected with which protocol. After that, Jason will cover MMT and the route in detail. Adrian will cover the specifics on the codec detail. Okay, so as you can see, this one is a head-end in the distribution chain. We call Atsc 3 in a distribution chain. On the left hand, all the content source, and then the encoders in between, and all the EAS and EPG and genetic data sources. Of course, the encoders connected to the packager and CNC, typically. So we, encoders drop the media in the form of MPEG dash, and usually it goes to the WebDAV protocol, and it feed into packager and the common encryption, or the encoders provide the MMT segment to the packager and the common encryption. Then we add the signaling. Mostly it comes from the user interface or in a configuration file. So we mix the Atsc 3 signaling and then ESG and NRT data, and then mux it, and then they pass to the scheduler. So in the end, the scheduler will transform all the media and scheduling data into the STL. So that in STL packets goes to the Atsc exciter and transmitter and off the air. This the diagram is a typical deployment of Atsc 3 in a distribution chain. I took an example of one of the Korean deployment the main station at the metropolitan area, and then multiple local stations. So here, as you can see, all those architecture components connected, and then so in the middle is a signaling and management in a server. So here, the blue line represents the media flow. It's starting from could be MPEG-TS or SDI input, and then transformed into packaged into route session or MMT, and then multiplexed with the signal and the other management data, of course, including the closed caption, and it goes to the broadcast scheduler. Okay, so here in a couple of slides, I'm going to show you the important architecture components one by one, and then spell out what would be the input, what would be the output. So starting from the signaling server, so like I said before, most of the configuration and controlling signals, ATSC signals, it comes from the user interface or the configuration files. And an output of signaling server, typically LLS over the well-known multicast IP, and a route and MMT sessions. And then the second one is the EPG server. EPG server, our EPG server, what it does is to translate the old EPG data to the ATSC3 compliant ESG in a format. So it comes from the our proprietary protocol fetching the EPG data, or combining user interface and the configuration data, and it actually output the guide delivery units and guide delivery descriptors to the multiplexer. And here is a multiplexer. So what multiplexer's job is, they're combining all different protocol sources in the MMT and media, the route and media sources, LLS and SLS signaling data, and then combine it into the broadcast scheduler. This one is a closed caption. Typical, it can typically, there are many closed caption sources depending on your broadcast stations. Some of them are proprietary. Some of them are all the cable closed captions. We can take the most of the formats and then output into TTML, ISO, BMF packaged, and route and MMT transmission. So it's compliant to the ATSC3 standard. So one of the important things is the packager, because packager actually it takes the media source and then create an MMT session and route session. And also we add the encryption at the end of the packaging. So in the end, you can get the protected route and MMT streams, and it goes to the multiplexer. So broadcast scheduler does the main job actually they're transforming all the media and data into STL. We have a very complicated process to compile into STL IP in the end. So essentially, route the out of the multiplexer, route and MMT sessions and LLS, all the ESG and the closed caption streams coming in, either UDP and the multicast. And then we, going through this process, actually we output the STL output to the transmitters. So here I explained most of the architecture component, and then now I pass it to Adrian, to get into the codec detail.
Now, Adrian Murtaza from Fraunhofer will talk about video and audio codecs.
So what I want to focus a bit more today is to shift from the transport layer a bit into the codec side and see what are the important aspects for ATSC 3.0 in order to enable all these new features through the new transport layer. If we go to the next slide, we will see here when it comes to the audio side first, ATSC 3.0 offers a complete end-to-end solution. So what is new, on one hand, the audio production, now it has to be object-based. Doesn't necessarily need to contain only objects, but you can have, for example, an immersive setup like 5.1+4 height speakers and 5 additional objects or any other configuration. But this is related to the production. So I will not talk about the sound production, but I will dive in directly into the authoring step. Because with all these new possibilities, of course, there is a need to control everything which is delivered to the end user. And for this purpose, we have developed together with partnering companies several real-time authoring units for MPEG-H audio. What these units do, they basically create all the metadata, so all the languages which are offered, all the features, dynamic objects, authoring, creation of presets, which are different flavors of the same content that the user at home can interact with, interactivity and personalization options. So the user can, for example, enhance the dialogue of the football game commentator, or to even move some specific audio objects in the room. Loudness and DRC control, which we know very well from the past. It's extremely important for ensuring consistent loudness across all programs. Now this is all embedded in the audio system, so you will never fail. And of course, all these options, you don't want to do them all the time when you go in live. You want to store your settings and just load them whenever you switch to a different program. And that is done through the capabilities of these authoring systems, which output the so-called control track. If we move on, the second aspect of this authoring units, it's of course the monitoring. You want to ensure that your content, it contains everything, all the features that you have created, and it sounds good on all possible outputs. So you want to switch in live between stereo 5.1 or a 5.1 plus 4 immersive setup and monitor all options. And also you might want to monitor the different interactivity options that you offer to the user. You don't have to test everything all the time, but you have all these capabilities integrated for live processing. And nevertheless, the loudness monitoring, of course, it's extremely important. If we move now to the encoding side, of course, on the video side, I will not talk too much about HEVC. Everybody, I think it's fully aware of the capabilities of the HEVC system, which is adopted by ATSC 3.0. And of course, the transport layer has already all the flexibility needed for supporting future video codecs. And when it comes to audio, I already mentioned the metadata, the authoring step, which is the key component. And that also, it's extremely important for the encoding step, because you want to ensure that everything that you have authored, it's delivered in a reliable way over SDI infrastructures, for example, to the encoder, and the encoder reacts and reconfigures itself on the fly based on whatever new settings you provide on the input. And on one hand, this is great because the encoder interface is now very easy. You just provide a metadata track which fully configures the encoder, and the encoder will do everything in real time. Of course, you don't want to run multiple encodings for all delivery formats and transport layers. And the key feature of the MPEG-H 3D audio system is that you can encode once, and then you can deliver the same stream over MMT, over route, over dash, and HLS streaming, basically on all possible transport layers. Okay, if we go now to the consumer end, we talked about all these features, but how the users can experience these new ATSC 3.0 capabilities. If you have an immersive system at home, either a soundbar or a smart speaker with 3D capabilities or binaural headphones, doesn't matter what's your consuming device, you still can experience the immersive sound. So you perceive the sound coming from all directions, and you can feel at home part of the audience. Either a football game or a music concert, you'll always get the full capabilities. Of course, immersive sound is only the first aspect. The next extremely important feature of ATSC 3.0, it's the interactivity. And on the next slide, we will actually see here a very simple user interface. This is implemented for a mobile application, but we've seen, for example, on the LG TV sets in South Korea, they have native support for the MPEG-H 3D audio interactivity user interface. And with such UI, you can interact with the content. So you don't consume the content at home in a passive way, like in the past with stereo and surround sound. You can now exploit the object-based approach. So what that does mean, for example, you can increase the level of the dialogue to your own preference. You can remove the dialogue if the broadcaster allows you to do that. You can switch between a live sport event, so you without any commentator and just enhanced crowd, or you can listen to your biased favorite commentator for your home sports team. All of these features, they can be enabled and disabled on the fly, and because of the capabilities of the system, everything is seamless to the consumer at home. So if you have an ad which is inserted on the fly, only as stereo, for the user, all these features will simply disappear and then come back when the content is back live, without any audio dropouts, without losing the signal. In a nutshell, I think that covers the let's say, most important aspects of the audio system. And I will now give the floor to Jason to talk more about the MMT and route solutions.
Finally, ONE Media 3.0 Sinclair Broadcast Group's Jason Justman will talk about broadcast and broadband delivery.
My name is Jason Justman, and today I'll be talking about Atsc 3.0, Transport and Service Delivery, A331, LLS, MMT, and Route Dash. I'm currently a distinguished engineer at ONE Media, and we've been very active in the open source community by releasing libatsc3, which is a reference implementation for a number of the Atsc 3.0 standards available on GitHub. Now, today I'd like to talk about 4 key topics. Number 1 is that Atsc 3.0 transport and service delivery is all over IP multicast. Number 2, a common entry point for service discovery called LLS. Number 3, linear AV service delivery, including non-real-time content and data delivery via Route Dash. And lastly, a robust media fragmentation-aware transport via MMT. Now, what does it mean that Atsc 3.0 is all IP multicast? From the perspective of the receiver, or what we commonly call the physical layer interface, it means that the decoded Atsc 3.0 emission is comprised of the individual IP multicast flows that represent a service. Whether it's MMT, a route with linear AV, or data, each individual service is provided on its own IP UDP flow. This is very different than common MPEG-TS mechanisms, which deliver one large multicast mux, which becomes very problematic to decode individual services from. Now, how does a receiver understand what services are available? Now, this is delivered over something what's called the LLS, low-level signaling table, is specifically in this implementation, the service location table. This LLS has a number of different signaling types, but most importantly, the one that we're interested in is the SLT, which provides information about the service, its name, its channel ID, but most importantly, it provides the destination IP and UDP for the multicast emission. The SLT also provides information about the protocol, whether it's route or MMT. When we look at Route Dash, it follows the common RFC standard for ALC, which is called asynchronous layered coding, and another RFC standard called FLUTE, file delivery over unidirectional transport. This is commonly used for Dash delivery of linear, live, and prepositioned content, and additionally NRT content, usually containing the broadcaster application or other data-based delivery services. Now, since Atsc 3.0 is built on IP multicast, it means we can use common tools like Wireshark to decode and understand what the transmission looks like. In this example, I'm looking at a ALC flow of a Route Dash service, and specifically I filtered it down to what's called a transport stream identifier of 0. TSI 0 is important because it contains the MBMS signaling or service level signaling information, which allows the receiver to properly understand the route emission and decode the services. In this example, we see 2 entries here, one containing a video emission and one containing an audio emission, and identifier information for the receiver to understand where the receiving IP multicast flow is and what the appropriate transport stream identifier is. When that all comes together, it means that receiving devices are able to play back a Route Dash emission, just like any other Dash payload. It contains a manifest, it contains the video, audio, and media fragments that are required for proper playback. Now, looking at MMT, assets, instead of delivering over like Route Dash via a unique transport stream identifier, They're identified via what's called a packet ID and type. Now, this looks much more complex than the route dash model does, but there's a very important reason. Now, at first glance, MMT follows the common ISO-BMFF box and fragmentation model, which looks very similar to route dash. But there's one important difference. MMT supports what's called out-of-order mode. This out-of-order mode allows the MDAT to be delivered before the MOF, which contains the track metadata. MMT provides, at the start of each sample, an MMTH sample header prefix, which allows us to understand its sample number, i.e. which frame, its offset, and its length to allow for robust depacketization and decoding on mobile devices. This is extremely important because there may be lost or dropped frames that would not otherwise be able to be recovered in route dash, but in MMT, the decoder can easily skip over them and still provide a linear AV essence for the viewer. Lastly, I'd like to show you a very quick demonstration of what route dash and MMT looks like on mobile, specifically on our Mark I ATSC 3.0 software-defined radio handset. So here's an example of us decoding a route dash linear AV service over ATSC 3.0. If you notice, there is a distinct channel change time because we have to acquire the individual components of the service level signaling and the individual media fragments. But with MMT, we're able to switch very quickly because we only are looking for the next iframe and don't have to wait for service discovery of the service level signaling. So what did we cover? Number one, ATSC 3.0 transport and service delivery is all over IP multicast, which provides a common transport mechanism between the physical layer and the receiver media processing stack. Number two, 3.0 services are able to be discovered using a common entry point through the load-level signaling, specifically the service location table. Number three, linear AV service delivery, including NRT and prepositioned content using route dash. And lastly, a robust media depacketization model using MPEG media transport, specifically for mobile use cases. There's quite a lot more to discuss in ATSC 3.0, but thank you for your time, and please feel free to reach out if you have further questions.
Thank you for watching our presentation. If you have any questions for our speakers, contact them through their email addresses you can see on your screen. I'm Josh Gordon, TV Industry Strategist. Thank you for watching.